Hello, today we will learn what is finite automata. So finite automata, it is also called as a finite state machines because it is works as a machine. So here it accepts a string as an input and produces the output accepted or rejected. Okay, so in the Greek word the automata means it's a machine. So here you can see this is a block diagram of finite automata where input is a string to be processed. Okay, to be processed is the stored in input, and this is a control unit. It consists of a state q0, q1, q2. So it consists of states. It can be any number of states. Okay, in the final state, and the current input symbol and the current state of the machine, it may change its states. So it may change its states. And secondly, we have an output. So output is the end of input. If the input string is accepted by the machine, then we encounter the state in the final state. But when end of the input is encountered and if the machine is not in the final state, then the input string is rejected by the machine. As we have seen, the output can be accepted or rejected. Okay, if the state is in the final state at the end after reading all the input, we call it as accepted. If it is not in the final state, then we call it as a reject of the string, means that is not been accepted by our design or the language. Now let's see some notations to design the finite automata. Firstly, all the states of the finite automata language will be starting with an arrow and the circle. So inside a circle we call it as a state. Okay, so here where there is a arrow which is not originating from any node represents the start. Okay, start state of the machine. And if the two circles are being used, then it is called as a finite state. If the string reaches the final state, we say it as a accepted. And here you can see the arrow going from Q0 to Q1, state Q0 to Q1, and it is labeled as 1. So this is your labeled as 1. So this is a transition occurs from Q0 to Q1 state. Okay, and here is a looping structure that we represent like this. Q0, it is taking transition for the input 0 to itself. Okay, so these are the transition. How to represent this transition? So here it's a delta is a symbol, transition function, and Q0 is a starting state. From starting state to the input 1, it is reaching to the Q1. So this is how we will represent Q0 for the input 1. When the transition happens, it reaches to the Q1. And for the loop, if the transition happens for the Q0, for the input 0, it will reach to the Q0 only, means itself. This is how you represent the transition. It can be written this way. Okay, and if you are reaching for the two input same transition, but here transition can be defined for only one single input. So here Q0 for 0 it is reaching Q1, and Q0 for 1 it is reaching Q1. The same way Q0 for 0 reaching Q1 and Q0 for 1 also it is reaching Q1. This is how you have to indicate the machine representation, the transition function. Okay, next coming to the types of automata. We have three types of automata. One is DFA, deterministic finite automata, NFA, that is non-deterministic finite automata, and epsilon NFA, that is non-deterministic finite automata with epsilon modes. So this is the three types of automata we will be discussing. Now, what is DFA? DFA is deterministic finite automata. What is deterministic? That means there is a exact only one transition from every input symbol from the state. So, it is possible to determine exactly to which state the machine enters in after consuming the input symbol. So, the machine is called deterministic. Okay, that means what? You can see this diagram. Q0 for 0, it is reaching Q0, and Q0 for 1 it is reaching Q2. Means for exactly one input symbol it is taking only one transaction. We can't write 0 here for the deterministic. Means what? One input, one transaction only per one particular states only. And second one, finite. As a finite number of states and edges. Okay, means that can be countable. Next, automata. As we have discussed, automata means it's a machine. So it's a machine which may accept the string or reject the string. So it is deterministic finite automata. Okay, or we call it as deterministic finite state machine. Okay, this is about the definition, means description of the name. Now come to the definition of the DFA. So definition of the DFA is this one. Okay, so in the short form it is a 5-tuple or quintuple indication of 5 components. M is equals to Q, sigma, delta, Q naught and F. Okay, so here M is a machine or the name of the machine, and Q is a non-empty finite set of states. The set of states, like what we have mentioned in the circle, no, all the that are the states which is in the finite, because it is a deterministic, we call it as a finite state. And sigma is the alphabet symbol, input alphabetic symbol, so which is also non-empty. Next one, delta is a transition function, right? And second one, nextly it is Q naught, it is a start state which belongs to the Q, means which is one of the states in the Q, starting state. And F is a final state that is represented by double circle. Okay, it is a final state represented by the double circle, which is also a subset of the Q. Since Q is a set of all the states, so Q naught will be the starting state, which is represented by the starting arrow on the small circle, and the F is a double circle, that is a finite state. This is the definition or 5 components of the DFA. Now, DFA is represented in 2 forms. One is transition diagram or a transition graph, we can call it as, and another one is a transition table. Okay, as we have seen, the 5-tuple representation of DFA is M is equals to Q, sigma, delta, transition function, Q naught and F. This is a 5-tuple representation of DFA. Now this is a notation. Consider this is a transition diagram. Okay, this is a starting state Q naught, and we have a 2 input symbol, that is 0 and 1. So we'll see the transition diagram of DFA has two states Q naught and Q1. So this can be represented in the capital Q, and there are 2 input symbols 0 and 1, that is our sigma alphabet, and the starting state is represented with the arrow, okay, not originating from any other state, so arrow. So that state we call it as a starting state, that is Q naught, and the final state represented by double circle, that is Q1. Okay, and the transition from state Q on the input symbol A to the state P is represented by A. That means here the transition is taking place, so that is with the 0 input, and another one is a 1 as a input. So that is called as a transition. So now how to write this transition? For the delta Q naught for 0, it is reaching to Q naught. Okay, and for the delta Q naught for 1, it is reaching to Q1. Okay, this is how you will represent the transition function. Okay, the same representation how we can do in the transition table. Now you can see we have a transition function delta, 2 input symbol 0 and 1, that is our alphabet, and Q naught the starting state, so we represent with the arrow, and Q1 is a final state, so we represent with the star. Okay, final state means double circled, so double circle state we represent with the star, and the starting state means which is not originating from any other state, right? Arrow is not originated from any other state, we call it as a Q naught, which is a starting state. Okay, now how to fill it? Q naught for 0, so Q naught for 0, it is reaching itself, right? So Q naught. Okay, again Q naught for 1, so Q naught for the input 1, it is reaching to Q1, so you will represent your Q1. Okay, same way Q1 for 0, so Q1 for 0, it is reaching itself, So Q1, again Q1 for 1, it is reaching to itself, so Q1. Okay, this is how we'll represent the transition table. So here number of states, it can have any number of states, in number of input. For every transition, for every input it has to take a transition, so it is called as a DFA. So this is a representation of DFA in the two ways, and you can write both the way in the for every problem.